This whole chapter is an intro to calculus, and we won't get to the fourth one on derivatives, but we'll go through the ones on limits to get some basic idea on non-limits. And so first what I want to mention, in algebra, you're really studying arithmetic operations. And with variables, but if you think about it, even though it uses the word arithmetic, that's an all-encompassing thing that includes things like multiplying, dividing, square roots, fractions, etc. So it includes multiplying, dividing, even though it has arithmetic as part of the word. In geometry, that's the study of shapes. And in calculus, let's see if I can spell it right. What we're doing is we're studying continuous change. Continuous change. So one idea, one way I want to show it, is if you have a curve. Well, at this point here, if you were to draw a line, a straight line through that point, that just touches, or what's called a tangent line just touches in one little place. There's a slope for that. If you do rise over run, you get a slope at that point. As soon as you move to another point on the curve, though, the tangent line is a little different, so it's a different slope. So every single point has a different slope. In other words, the slope is changing. On a straight line, a linear line, like the tangent lines that are drawn, those lines are straight linear lines where the slope never changes. What calculus does is it studies what happens as the slope changes around the curve. And it uses that for various applications. One of which, for instance, is to find the area that's underneath the curve. And that's also used in engineering and some things like that. We're not going to go too far with it. But we are going to be talking about finding the limit. If we pick a point here, the limit as this curve gets to here this way, and as you come up the other way. So we'll be seeing what happens with that. So, and in fact, I should determine I should go through the word limit, because that's what we're studying for the first three sections of the chapter. And what that is the number you approach from both sides sometimes can't touch it. In other words, dividing by zero. So you'd have something where you'd have to be dividing by zero, so you can't, so therefore you can't touch it. But in other cases you can. That's why it's sometimes. So what happens, let's take the way that this looks. The limit of the function at x as x approaches a. Now I actually didn't need to draw the line under it, so let me rewrite it just to write it normally. The limit of f of x as x approaches a. So x is whatever the variable is going to be. It could be n and n. But a is a number. Usually you see x approaching 2, or x approaching 0, x approaching negative 17, something like that. And then you'll end up using it. So I guess we'd say, let's write this out. As x gets closer to a, but still is not equal to a, the corresponding y values, let me explain that in a moment. I put the f of x results. The result, when you have a function here, when you put it in x, you get a y, but that really is just, it's a result. Let me make sure you can actually see those words that were results. So those results, the corresponding y values, get closer to the limit. In the example we're about to do, you will see that happening. We'll start changing the x, and as the x gets closer to some number, to get closer to whatever this a is, you will find that the y values get closer and closer and closer to some number. So let's do that. You may already have seen this in this first section of the book, but you're going to have to do one of these on the test, so we go through one. So we'll call this essentially part 2, because all this stuff's part 1 of this. Limit of 2x squared as x approaches 5. So let's make a chart. Watch what I do up here first. So you can see what I'm going to want is 1, 2, 3, 4, 5, 6, and 7 places. 1, 2, 3, 4, 5, 6, 7. Okay, go ahead and put those in. And then here are the numbers that we use. 997. 4.998, 4.999, nothing in this one, 5.001, 5.002, 5.003. So you notice the x values are going up, and if we start here, come this way, the x values are going down. So we are getting closer to the 5, much closer, very, very close by going like this. If you put this in the calculator, put in that number, square it, and times 2, and same thing with each of these, here's the numbers you get. 49.94, 49.96, 49.98. So here, what happens is you get you're 0.06 away from 50. You're 0.04 away from 50. You're 0.02 away from 50. I have a feeling what's going to happen if you keep on going. If you get closer and closer and closer, you're going to get closer and closer to 50. And this way, it's the same thing. If I'm at 5.03, I have the number 50.06. This is 50.04. This is 50.02. Next should be 50.0, just like coming up is 50.0. So it looks like you're coming this way closer to 50, this way closer to 50. That means the limit is equal to 50. So what we do is we put that after this. So we would say the limit as x approaches 5 of 2x squared is equal to 50. Now in this case here, if you were to put a 5 in here, 5 squared is 25, times 2 is 50, you can see that. And in section 11.3, that's this is actually one of the properties usually, so you can do it. But it was good also to see it this way. And I'll tell you that there are some of them where you can't just put that in. If this was dividing by x2, or by x also, then putting a 5 in there would have given you an impossible situation. And only this, or a graph of it, would show you where the limit would be. And we're going to do that with the next one. So let's call this 2a. And for 2b, we're going to find the limit as x approaches 0 of the function sine x divided by x. So we want is to find that limit. So when you look at this here, if I put 0 in here, like up here, I could put 5 in and I would get to 50. If I put 0 in here, I'm sunk. I can't do that. So for this, we're going to use the calculator, because this is another one of the things that's good to see how you can use the graphing calculator to do it. So let's pull that out. Now, I don't really care about graphing it, because, you know, if I put in the graph, I might be able to see something, but these aren't good graphs. What I want to do is I want to use the table here. If I set up the table so that I have a number of x's, and then it gives me what the y values are, And what's going to happen is I'm going to see where the y values start coming closer to each other. So these are the numbers already set for the table, but there's no y's in here because I don't have an equation. So I'm going to go here to this one, and I'm going to enter the equation of sine x. Because remember, this is the limit of the function of x, and there's the function, and that's 1. So we put sine x divided by this. Sine x, this time I have to use parentheses, and we'll divide that by x. And sometimes people might want to be extra safe, put parentheses around the whole top part. I'll show you what that looks like. I sort of like doing that even though I don't need to for these. Now I know for sure that that x is on the bottom and everything is on top. Yes?
Mine has R instead of Y, and I forgot how to change that back.
I'll show you. The reason why it is, great question, because it's all based on the mode. Because what I was next going to do was the mode. When you're doing a trig one here, you have to be over the mode, you have to be in radians. You are also in polar. You used that recently to do a polar problem. So you want to go down here, move it back to function. But you also want to move degree over to radians. You want radian and function. When you see R, that's the radius for a polar one. And it's nice that they do that. The good thing is that you realize too that you need to change it. At least they show you there. The radian ones, you don't realize it till it's too late sometimes. So now do you have radians and function?
Yeah, now it's
Great.
good.
So come on back. That's a really important thing to think about because so many times on various tests, being in the wrong mode messes up an answer and you don't even know it. So it's a good thing to be aware of, and now you see how to change it back into those. And the basic rule of thumb for radians is whenever you're graphing any trig function, then put it in radians. All the other times, not radians, leave it in degree. This is the only practical time that we're doing it. Okay, now that you have that, you can graph it if you want. I press graph and it gives me not much of a graph. That's not really that helpful. I could change the window to make it look different, but I didn't come to it for the graph. I came to it for the table. So press the second function and table up here, graph, and this is what you want to see. Now you may not see these numbers, okay? What's your starting one that you have there?
-30.
Okay, here's what you want to do. Good, I'm glad, because that'll show you change it. Go to second and window, because that's table set. Do you see this? Yep. So for the table start, put like -0.3, -0.4, -0.2, something like that. Something that's just below 0, but 1 decimal point. And then put a 0.1 for the table change. What that'll do is it'll change, it'll start with this -0.3, then do -0.2, then do -0.1. In other words, now, if you go back, you should be able to see where 0 is. Okay, cool. Now, what's happening is we're getting closer to 0 on both sides, because remember the limit's 0. So when you go closer to 0 with the x's, look at what's happening with the y's. 0.98, 0.99, 0.998, error, can't divide by 0. But you're getting pretty close to 1. And then if you come the other way, same thing. Coming from both of these ways, if you didn't have an error, it looks like both of these would have gone to the number 1 and they would have meant 1. It's almost like you're going up to 1, coming down either way. But clearly that should have been a 1 if it wasn't an error, because you're getting closer and closer to the number 1. That means that in a calculator, you're finding out that the limit as x goes to 0 of sine x over x is equal to 1. That would be the limit. I rewrote it just so you can see. We're trying to figure out what it is. You put it in the calculator, and then you can use the this thing. In fact, I'm going to do a little, just because this is on video too. I'm going to show the numbers too. It was this -0.2, 0.99335, -0.1, 0.998. You get the idea. 0, it's an error. At 0.1, it's 0.9983835, and you say. So basically, you can see that, you can see you're getting closer and closer to 0, and when you do, you're getting closer and closer to 1. So the x's are getting closer and closer to that number from both sides, and then the y's tell you what the limit is. So that's the way you can use a table. Right? If there's time, we'll come back to one because we have the same kind of one. Actually, let's do one where we just do it on here. So let's practice without having to draw it out, although you are going to have to, on my test, I'm going to make you do at least one of these. That doesn't hurt to check it with the calculator. So let's practice with this. The limit as x goes to 0 of 4 sine 2x over x. All of that. And close that parentheses. Oh, bunches of parentheses needed this. So parentheses 4 times 4 7. So you should get something that looks similar to that. Did you? Cool. So that means putting it in. I put a beginning parentheses, which I really didn't need to put in, but I like to be safe. Now when you get this, since I hit graph, I have to wait till the whole thing goes through. And the graph doesn't necessarily help you because you can't get in to see what that it jumps over 0 at a certain number. Actually, it jumps over at 8, 7.9, 7.9 from both sides. So as you get closer to 0, you're getting closer to 8, so the limit is 8. So we'll come back over here and we'll put equals 8. So that's a way of figuring out the limit that is using this. You just let your calculator do it for you, which is another nice use of the calculator. Now, part of what this means, right? So this is like the calculating part you need to be able to do. You need to be able to do it by a table, and you can use a calculator to make the table. You also have to be able to find the limit graphically, which is not that bad. Let's take a look at a couple of things. And some of this one part you can find in the textbook because it's not a hard one. I'm going to go through a couple of examples from that. Find a limit using a graph. So let's do just a simple basic one with no numbers. And I'm going to have a curve here. Oops, but I'm going to do an open circle at one point that the curve comes to and stops, jumps over and continues. So this, what we're looking at, remember the x values, like limit of going to something, that's the x value. So if I go out here, I'm going to call this a. And remember that these always look at limit as x goes to a, whatever that would be, of whatever the function is. This could be anything in here. When we do function of x, what we're saying is something, like sine x over x, or 2x squared, or whatever it is. It's some kind of binomial, or trinomial, or whatever, binomial. So we don't know, we don't really care what this is. This is clearly a curve. It's probably x squared plus 3x minus 17. I'm going to make a guess. But what happens is when you go up here to a, this is the x value. When you go over here to this way, that is L. So in a way, you can think of that as A and L, as x and y. But that makes sense because remember way back when you were taught at some point that the y value or the f of x is actually a dependent variable and it depends on this. So this forces that. Okay. We don't usually write it that way, so that's not as common, not commonly written that way. Normally we do this. The limit as f of x The limit of f of x as x approaches a is equal to L. That's usually how we write it. And so you can see it just on a graph. Now, I am not good enough at drawing a million graphs for me to write them all up, so we're going to look at a couple. So here's where I got that basic thing. On A, up to here, that point, go over to the y value, there's L. Okay? And this one is showing that as you get closer to it, right, well, you can actually be at it because it's a filled-in circle. It's a legal part of it. You know, whatever A is will not be dividing by 0. Here in this case, whatever A is will make you either divide by 0 or something like that, so you can't even include that. Okay, so what it's still the same thing. You say the limit is L. I forget how they show it down here. F of A is L. Okay. So even though at this point, like say that was 12 here, A is allowed to be, or the limit is 12, and if you put A into the function, you'll get a 12, no problem. Here, if you put the A in, you get a undefined. You'd be dividing by 0. Over here on this one, you would be dividing by 0, except that you wouldn't necessarily, because they have usually two functions, and one of them is at A, use this number up here. So as you get closer and closer, you're getting closer to that point, so the limit will be that, but the actual result of using the A would give you a number like here. Like if that were 12, then the limit would be 12, but the function at that number would be 17, or whatever that is. And that's actually part of 11 into 11.3. We'll be doing that one in a moment, but that leads to that. Leads into it. Right now, this graph I like. I'm going to point this one out. See how far we can get here. Aha. So let's look at the choices here. There's two of them where for -2, the limit at -2, you're coming from both of these and you're getting closer and closer and closer to 5. So the limit is 5. Problem is, even though the limit is 5, the function when you use -2 will give you a 3. And let's see, which ones of these? And here. And we'll do it 4. You're doing two things. The limit at 4, so as you get closer and closer and closer, as you get closer to 4 here and get closer to 4 here, the y values going along here get closer to 7. So the limit as x approaches 4 of this function, whatever it is 7. But the function, when you use the number 4, actually gives you a dot down here at 2. If there wasn't anything here but this, you would have to say that there's no solution to that. So if this didn't exist, because that's an open circle, the answer to this would have been no solution. But because there's actually something given to you that's a legal point, then that means the function, when you use 4, calculates as the number 2. And this is called discontinuous. It doesn't continue. You go one way, you have to go somewhere else and then come back, and they're not actually touching. All right, so those are good examples. I really like this one. You have it in two cases like that. And then down here, you have, on this one back here, you actually can see where sometimes the limit is actually the result of the function 2. Sometimes there is no other point. So at A, you can't either say no solution, but you say that the limit is whatever this number is. And here you have it like the example on the next page. Okay, so being able to find the limit by a graph or by a table, that's what that section was.